Welcome, everyone. Pleased to have you here with us today for, I believe, our 64th episode of This is CDR. This is CDR is an online event series presented by OpenAir to explore the range of carbon removal solutions currently being researched, developed, and deployed, and to contextualize them for policy proposals OpenAir is working on advancing in pretty much every level of government here in the US, as well as in national and subnational jurisdictions globally. My name is Toby Bryce. I work on policy advocacy and market development for OpenAir, based in Brooklyn, New York. If you haven't done so already, please introduce yourself in the chat and make sure you're directing that to everyone and tell us where you're zooming in from. Just some quick background on OpenAir. We're a distributed volunteer network dedicated to advancing carbon removal solutions essential to solving the climate crisis. We're a global community. We work together on what we call missions, which are open source projects in the areas of research and development, messaging and communications, policy advocacy, and activist market development. We'll put a couple links in the chat to just illustrate the kinds of missions we work on. Here's a little graphical illustration of them and a link to join our group. We'd love to have you be a part of what we're doing. So kicking off today's program, before we get started, we always like to define our terms. This definition of carbon removal is from the CDR primer, which is an excellent resource for learning about CDR. It's also essentially the same definition that the IPCC uses, most recently in their published synthesis report, which came out yesterday. Carbon removal is purposeful human activity to remove carbon dioxide from the atmosphere and to durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. Two really important points to call out when you talk about carbon removal. Number one is to disambiguate it from quote unquote carbon capture. Carbon capture typically refers to point source carbon capture, meaning capturing CO2 from an emission source like a natural gas power plant or a cement plant. This may or may not be a good climate solution, depending on the specific techno-economic, socioeconomic, et cetera, conditions of a given project. But one thing it's clearly not is carbon removal, which again is removing CO2 from the atmosphere and durably putting it away in storage. Number two, whenever we talk about carbon removal, it's really critical to call out upfront, loudly, unequivocally, that CDR is in no way, shape, or form a substitute for reducing emissions. We need to reduce emissions and decarbonize our global economy as quickly and as completely as possible. Organizations like Science Based Targets, they postulate that at least 90% of our climate work in terms of reaching net zero needs to come from emissions reduction. But there's clear scientific consensus that we are not going to be able to reduce all of our emissions in a climate relevant timeframe, for example, from agricultural systems, which are a third of global emissions. It's not going to be possible or equitable to completely eliminate those by mid-century. And there's clear consensus from the IPCC and elsewhere that we're going to need carbon removal at gigaton scale by mid-century. Right now, carbon removal, long duration carbon removal is at kiloton scale. So we have a lot of work to do, many orders of magnitude to traverse to get to where we need to be by 2050. And it's really important that we get started on that work now. And that's one of the purposes of this series, is to learn more about carbon removal and talk to the folks who are actually doing it, which is why we're here today. So I'm going to hand it over to my colleague, Megha Raghavan, who's going to speak a little bit about the run of show, and then she will introduce today's speakers. Megha.
Hey everyone, I'm Megha. I'm an OpenAir member based in London, and I work on policy and market development as well. So as usual, we're going to start with a short presentation, followed by a few prepared questions, and then moderated audience Q&A. So if you have questions along the way, please type them into the Q&A box in Zoom. Just note that's separate from the chat function, so just find the one labeled Q&A to help us organize things a little bit better. We'll send the video link out to everyone who registered, and we'll also post to OpenAir's website and to our YouTube channel, where you can also find all of the previous episodes. This week on This is CDR, we're very pleased to welcome Kodama Systems Head of Biomass Utilization and Policy, Jimmy Voorhis, and Yale Carbon Containment Lab's Associate Director of Science, Dr. Sinéad, who will discuss their research collaboration on biomass burial of unmerchantable residues from fire thinning. Jimmy leads biomass utilization and policy at Kodama Systems, where he develops solutions to create value from forestry residues based on their inherent carbon. Prior to Kodama, Jimmy was a consulting geochemist for international mining companies and built water and mass balance models of major mining systems across resource types. He is an expert at developing methods to better constrain earth processes and has pioneered studies in sulfide mineral electrochemistry, as well as characterization of pit lake water quality and dynamics utilizing aerial drones. Previously, he was an ice climbing and mountain guide in Alaska and a National Geographic explorer studying the impacts of climate change on winter recreation. He holds an MS from Dartmouth and a BSc from Tufts. Dr. Sinéad Cruddy has 10 years of experience in experimental community ecology, ecosystem restoration, and environmental engineering. Her previous work utilized primarily hypothesis-driven field experiments, along with regional survey techniques, geospatial analyses, and modeling efforts to investigate the effects of climate change on biodiversity, stability, and functionality of coastal ecosystems. Sinéad has conducted research across the many coastal ecosystems of the eastern US, including salt marshes, sand dunes, mangroves, cobble beaches, and live oak savannas. She holds a PhD from the University of Florida in environmental engineering sciences in 2019. And prior to her dissertation work, Sinéad received her Bachelor of Science in Biology with honors from Brown University in 2015. So presenters, whenever you're ready, over to you.
Wonderful. Thank you so
Thank you,
much.
Mega.
All right, off you go, Jimmy.
All right. So thank you everyone for joining today. A real pleasure to be here. I'm Jimmy Voorhis, head of biomass utilization and policy at Kodama Systems, where we seek to increase the pace and scale of forest restoration by developing automation tools to increase the productivity of thinning treatments and developing the bikers ecosystem.
And huge thank you to Toby first and the Open Air team for the invite. My name is Sinéad Cruddy, and my background is in experimental community ecology and environmental engineering. I'm the Associate Director of Science at the Yale Carbon Containment Lab. We were founded in 2020, and we are a part of the Yale School of the Environment. And at the CC Lab, our directive is to research, develop, and implement low-cost, safe, and scalable approaches to carbon removal and containment. And I'm very excited to talk with you today about one of our carbon containment projects.
Great. Sinead, if you could kick it off here. Perfect. So today we're going to be talking about coniferous forests in the Western US. These forests are largely overstocked and overstressed. Traditionally, a few hundred years ago, Western US forests were patchwork mosaics of mature forests separated by meadows, and historically we really had short fire return intervals. On many places in the Central Sierra, for example, were on the order of 3 to 5 year burn return intervals. And these are typically burns that were started naturally, or they were regular cultural burns by indigenous peoples. Beginning in the late 1800s, cultural burning was criminalized. Many forests were intensively logged. And then in the early 1900s, the policy of fire suppression began, which allowed, as you can see from these photos, for a massive biomass accumulation versus these traditional patchwork mosaic conditions. This dense carpet of forests means that trees need to compete today, and that there are, with the influences of climate change leading to drying and pest outbreaks, massive fuel loads accumulating. This leads to really high risk conditions in these forests. So these high fuel loads lead to intense fires over large areas. These are known as mega fires that burn up to and over 100,000 acres in each fire. They grow and they move really quickly. Mega fires in their wake can sometimes cause complete landscape conversion, where there's risk of forests entirely converting to shrublands due to non-existent or slow tree recovery associated with seed bank sterilization from the heat of the fire and few remaining trees. They impact communities and economies really significantly. In 2020 in California, there were $20 billion in economic damages, and that included $2 billion of suppression costs. And they also have a huge carbon impact. So the approximately 125 million metric tons of CO2 that was released in the 2020 fires in California alone was the second largest emission source in California that year. It was after transportation, but before industry and electricity production. So second largest source of emissions in the state, really amazing. The fires that year burned about 4 million acres of forest land, which, if you can believe it, was similar to the total annual burn area in this traditional patchwork mosaic. So it leaves the question, why is there such a difference in scale and damages? So one part is that we have a lot more assets in fire-prone areas today. Another part, and the primary factor, is that it's the intensity of the fires caused by this dense carpet of conditions. On the top left, you'll see the dense carpeted landscape, and trees are really close together. There are ground fuels, there are ladder fuels, which allow flames to grow up into trees, and then this growth of fire allows for these crowns of the trees to entirely incinerate, which leads to high tree mortality, near total, and this is that near total landscape conversion sometimes. However, if forests are thinned to their traditional densities associated with these pre-settlement landscapes, we can reintroduce restorative fire that burns close to the ground, removes the surface fuels, and preserves the big healthy trees, which don't have to compete and don't face as much water stress and are generally more resilient overall. And therefore, they can keep growing and are less prone to loss of their carbon. So we know what we have to do. We have to remove biomass and restorative forest thinning treatments and take out these small diameter fuels and thin, in some cases, the dense canopies. And there's ambition and broad public support to do so. So the US Forest Service has already committed to 20 million acres of thinning and additional treatments across federal lands by last year. But in 22, they released this wildfire crisis strategy, which aims to conduct an additional 20 million acres of treatments on federal lands, in addition to 30 million acres on other federal, state, private, tribal lands. So that's 70 million acres total over the next 10 years. Planning is ongoing for these efforts, and as you can see on the right, there's lots of mapping which combine parameters like risk to communities, biodiversity, water supplies, that's overlaying with fuel loads. And the federal government and states are committing really significant resources to figure out how exactly you're going to at least double the pace and scale of forest thinning treatments in the West. And there are a couple of hurdles to this that it's worthy to discuss here. And this is the problems that Kodama's focused on solving. So the two primary blockers to increase pace and scale is, first, the forestry labor force is shrinking at a time where we need to be at least 2 times as productive as it is today. And this is going to require skilled workers operating in remote areas or methods of enabling workforces to do more with less. And so this particular blocker, Kodama is developing automation tools to help solve around and to ameliorate. We're not here today to talk about forestry labor, though. We're here to talk about biomass carbon removal. And so the second blocker is the lack of non-merchantable biomass utilizations. In a moment, Sinéad's going to talk to the scale of the biomass available on the landscape. But quickly, I just want to say that the biomass piles that are produced as a byproduct of forest thinning treatments today, these consist of low-value materials like unmerchantable logs that maybe are pest killed or fire damaged. They're small diameter trees that don't really have value as in traditional lumber markets. They're branches and needles, and they're all good carbon. And so the additional cost to pile and burn these materials is about 10 to 25% over the cost of forest restoration treatments, the cost of conducting these thinnings. So there are significant added costs in addition to what's already going on to remove the material. In addition to that, they need time to dry out, and then they need a season to burn as well. So typically, the stack of forest restoration is thin, build piles, burn piles, and then broadcast burn. That's a large landscape burn to reduce surface fuels. And if you are able to remove these biomass piles from the forest, then you can reduce the actual time it takes to conduct that stack by just doing the thinning, removing the fuels in that same season, and then doing the broadcast burn. So you can bring restoration treatment from 4 to 6 years to really about 2 years, and remove the 1 to 2 years of curing and 1 to 2 years to conduct the pile burns that's needed today. And so this is one of the biggest things we can do to increase the pace and scale of forest thinning while reducing the cost. And Sinead, why don't you go ahead and talk about how much biomass there is out there?
Sounds good. Excellent, Jimmy. As previously mentioned, there are some very large commitments to restore Western US forests, totaling 70 million acres over the next 10 years. And while some portion of this biomass is merchantable, as Jimmy mentioned, a large portion of it is this low value, small diameter material, and options for its utilization are limited. So to understand the scale of this problem or opportunity, the first question we wanted to address was how much biomass carbon will be made available by these forest restoration activities. And so this was work that was conducted in collaboration with Nicholas Dahl, a CC Lab intern, and Anastasia O'Rourke, one of our managing directors. And to address this question, we compiled data from the Forest Inventory and Analysis groups, that's the FIA at the county level. The FIA is essentially the census of America's forests. So in the graphics at the bottom here in the green on the left, you see the distribution of forest land in the United States. And on the right, you see the distribution of FIA forest land plots, the 130,000 of them in total. And you can see a near complete coverage of the United States. And each of these plots are remeasured every 5 to 10 years. So it's a wonderful data set to assess the stock of carbon and above ground biomass on the landscape. So for this analysis, we included all Western US states from their most recent time point from FIA data collection, including Alaska. We then excluded some forest lands based on their accessibility or inaccessibility. So basically any forest lands that were greater than 40% slope or farther than half a mile from a road, we excluded from the analysis. We then ranked each county based on its wildfire hazard potential. So starting with the counties at highest risk and then including additional counties in order of decreasing risk until we reached 40 million acres of US Forest Service lands represented and 30 million acres of other federal, state, tribal, and private forest lands. So that's the 70 million acres that currently is planned to be thinned over the next 10 years. And then once we had this selection of counties and forest land, we set a few assumptions around stocking level and diameter of biomass that would be available in these sort of underutilized forest residue pools. And what we found from this analysis was that there are over 2 gigatons of carbon dioxide equivalents represented in these non-utilized or underutilized forest residue pools. What we see is that the majority of these are coming from California, Oregon, and Washington, and to a lesser extent, Idaho and Montana. And when we zoom in on the county level, you can see that a large portion of this biomass, of this material, is located east of the Sierra Nevadas. And it's a similar story in the Pacific Northwest, east of the Cascades. So it's these more sort of dry forests that are at highest risk and where there's a lot of biomass, a lot of this low value biomass that can be removed. So given that this is a substantial pool of underutilized biomass, our next step was to try and assess the carbon counterfactuals, or in other words, what is the fate of this carbon in business as usual? So just taking a step back, sort of high level, we know that trees draw CO2 from the atmosphere during photosynthesis, and they form biomass. This CO2 that they pull out of the atmosphere can be released into the atmosphere again through a couple different pathways. One of those is respiration, but other pathways are decomposition and fire. And these are natural pathways for the carbon that is derived from photosynthesis to re-enter the atmosphere. So how does this apply? Well, when we think about forest residues in question, there's 2 main pathways for their sort of fate. One of them is to be left in a slash pile. One of the issues with this approach is that this biomass is then vulnerable to future fires, so it's fuel essentially. And this carbon does decompose through time, and in that process, re-releases carbon back into the atmosphere. So I have a graphic here from Matthew Russell's group. This is data that was published in 2014. On the x-axis, you have years, and on the y-axis, you have proportion of biomass remaining. And what you can see is that after about 100 years, there's less than 10% of the biomass remaining. I will highlight that there are some above ground storage techniques that have been proposed in this field, and their goal is to very effectively slow this rate of decay. But today we'll keep focus on woody biomass burial. So another potential storage opportunity, or another potential pathway for this material, is pile burning. One of the benefits of this approach is that it removes that fuel from the landscape, so the surrounding forest area benefits from this reduced wildfire risk. However, one of the issues with this method is that it does release the vast majority of the carbon from that biomass directly into the atmosphere. So both of these options lead to a substantial portion of that 2 gigatons of CO2 equivalents being re-emitted into the atmosphere. And so one potential alternative use of the biomass is bikers, or biomass carbon removal and storage. This is a term that was coined by David Sandelow and colleagues in 2021 and includes a range of processes that use plants and algae to take CO2 out of the atmosphere through photosynthetic growth and store that CO2 underground or in long-lived products. So effectively, it circumvents this pathway of decomposition, respiration, and burning, re-releasing that CO2 into the atmosphere. So this range of processes includes a variety of feedstocks, such as waste biomass, like the residues we're talking about, but it can also include dedicated biomass crops and algae. It includes a wide range of conversion processes, which can be biochemical, thermochemical, or other non-energy conversion processes. And it typically has one of 2 forms of outputs. Some bikers pathways generate an energy product, such as syngas and biofuels, but all bikers pathways generate a carbon product, which can be in a variety of forms. It can be gaseous CO2, it can be bio-oils, biochars, or it can even be unaltered biomass, such as what we're talking about today. But ultimately, the net carbon effect of any of these biker systems depends on the conversion technique and also the durability of the storage approach. So what we have here is a graph of carbon effect. So this is measured as the tons of carbon stored or avoided divided by the tons of carbon present in the initial feedstock. And what we see is that different biomass utilization pathways range in their carbon effect, as well as the costs and the durability of their carbon product. So I'll note that both the cost and the durability are not noted here. So effects range from pile burning at the lowest end, where most of the carbon from that feedstock is re-emitted into the atmosphere, to biohydrogen production with carbon capture and storage, or CCS, on the higher end, which is at least in large part driven by the displacement effect. I'll also note that biomass burial, as it's calculated here, compares particularly well to other uses that generate emissions in their conversion process, such as biochar production. But this carbon effect does depend on the durability of the storage approach, which begs the question, what storage opportunities exist in the US? So orienting you here, we have a graphic from Sue Hovorka's group detailing potential geologic storage opportunities in the US. And while there are a great many of them, there are limited storage opportunities in the regions of greatest interest for forest restoration. So if forest residues in this area are to be utilized, a new approach may be required for storage. One option in this region is the Columbia River Basalt Group, which may be a key resource in coming years. But until then, another option is biomass burial. It's a relatively simple idea proposed in 2008 by Professor Ning Zhang. And I just want to give a shout out to Professor Zhang. If you haven't seen his open air, this is CDR presentation, I highly recommend you check it out. The YouTube link is on this slide. The basis of this idea is that essentially when you can create anaerobic conditions or remove oxygen, you can limit the majority of biological decay. So there have been examples found in nature of buried wood samples, particularly in locations where there weren't allowed to be intermittent cycles of wet and dry and where the conditions were particularly anaerobic. And through those examples, we've seen carbon stored for several thousands of years. And so this has inspired a whole suite of CDR projects related to biomass burial and or sort of storage and prevention of decomposition. And the approach does vary by environmental context. So for example, Carbon Lockdown, Dr. Ning Zhang's group, is focused on clay-lined vaults. And the idea here is that the grain size of the clay is so fine that it permits, or it does not permit, any sort of water percolation or gas migration. There are some alternative approaches, such as what you'll hear about from Jimmy in a moment, and what Kodama is focused on, such as evapotranspiration covers. These have a long history in the landfill literature and are particularly effective in arid environments. But across all of these approaches, a key uncertainty is methanogenic bacteria. These are bacteria that degrade wood in anaerobic environments, and they generate methane, which is a really important thing to understand because methane has a higher global warming potential than CO2. And so understanding where it's emitted and at what concentrations will be critically important for assessing how effectual these treatments really are. And so I just want to point out that there is MRV deeply in development, and field trials are critical to assessing under what context and conditions biomass burial may be an appropriate woody biomass solution. So with that, I will transition back over to Jimmy to talk about the pilots.
Thanks.
Jimmy?
Thanks, Sinéad. Yeah, and we're just going to talk a little bit about Kodama's earth and wood vault design here and these ET covers. So Kodama's design relies on moving wood from forests to arid lands nearby, and that's rangelands, so shrublands and deserts adjacent to these forests. So at the forest thinning treatment, we take an extra step of processing small diameter bolts. So those are the tree trunks, the small diameter tree trunks that are typically stacked in piles and burned. And then we load them onto trucks, transport them to our vault sites. And then we essentially, in an excavated pit where we remove a few meters of fine grained soil, we deck the logs like you'd see at a sawmill, for example. And we progressively do this and cover over the wood deck using the same earthen materials that we removed to do the excavation. And then after we reestablish this soil cover, we revegetate it using native shrubs, native vegetation. And this is an important point. We want the final cover, the final landform to look exactly as it did before, essentially, except it's now mounded. It's a structure that's made of wood and soil and vegetation. So the image in the top right is a active ET cover, evapotranspiration cover at a uranium tailings facility in Monticello, Utah. As Sinéad mentioned, these types of ET covers are deployed widely across the Western US at mine sites and landfills, and they are best practice for long duration waste containment. They have got a design life of 1,000 years, 1 millennium. And they, the covers themselves function with the climate, the dry climate, to prevent water and oxygen from penetrating down through to the wood mass. And it does this in a few different ways. So first, the cover soil itself, as you can see in the right, there's a little cross section of the cover. The cover soil absorbs water, and then the top will evaporate over time, the bit near the surface. The plants on top, were adapted to these arid conditions, send out a lot of roots after they're established, and they scavenge water to really great effect and then transpire nearly all the water that does not evaporate. This maintains a zero water balance to the wood mass and prevents water transport of oxygen down to the wood. And then that thick fine-grained soil cover also creates really tortuous paths for gas transport. So both oxygen has this difficulty moving in at a fast rate, where gases produced in the vault have a difficulty moving out. And this is important when we think about methanogenesis. So not only does this barrier, it's not an impermeable barrier, but it's a very slow diffusive barrier that enables anoxic conditions to be created in the vault around the wood mass. And any methane that is produced from the degradation of available organic carbon in the wood mass is likely to create, as Sinéad pointed to, methane and CO2 in equimolar parts. We anticipate that the rate of generation inherent to the wood, as we've observed through the biofuels literature, as we've observed through anaerobic digester studies in the landfill literature, that the rate of generation of this methane will be significantly less than the rate of oxidation that's present in the top portion of the soil cover, that is oxic, that has roots, that has high microbial activity, and importantly has high rates of microbial activity, including methanotrophic organisms which occur naturally. These have been observed at landfills and other arid sites. For anyone who's interested in the conversation around methanogenesis and methane oxidation, I highly recommend you read these sections in our frontier application because we lay this out in great detail. I just want to say one note on an MRV. So we are closing the mass balance with this approach. So we measure for the wood mass, carbon content, moisture content, and total mass before the wood, that's carbon in. That's our mass that we're measuring against. We're also planning to track the measurement and loss of soil carbon and methane and CO2 fluxes through the soil across the surface using distributed flux chambers that can resolve emissions above natural background levels. And so this enables us to essentially do the mass balance and we believe get an accurate measure of the total carbon storage via this method. And so folks really want to know about numbers. We've done an LCA and we've estimated costs for the pilot project and for larger facilities. And so really the machine emissions, I think this is something that's quite surprising. The machine emissions associated with processing, moving, and constructing the vault to store all this wood are not a huge additional emission, right? So it's about 5% of the total that we anticipate of the total carbon stored in the wood that we anticipate emitting in development of these facilities. The decay losses, we have here a range of 2% to 10%. 2% is the amount that's been observed in some of our anaerobic digester tests, has been observed in certain studies in the landfill literature, and we are evaluating against. We think it's going to be around 2 to 3% decay losses at 1,000 years. And there's a number of studies that we cite in our app that are cited in our frontier application as well that I would direct you to if you're curious about where that number comes from. 10% is the IPCC default factor for wood storage and landfills. And using this range, we get a net CDR of around 85 to 95%. Now, I will note that this doesn't include the counterfactual scenario, but I'm happy to talk about that more during the questions. And then relative to costs, the pilot, we are selling to Frontier for around $600 per metric ton CO2 equivalents. And then at scale, we think we're going to be sub $100 a ton CO2 equivalents. And then just to dovetail off of Sinéad's comments about scale and the deployment potential. So we think that wood vaults have an opportunity to deploy exclusive of sequestration basins, which if you remember back to this Forest Service landscape priority treatment areas, this is an area that really meshes well with where we need to take wood out of forests, right? Where we need to take this biomass out of forests. So we think this is widely deployable in the arid west and areas that are complementary to landscape scale thinning treatments. Wood vaults also have the potential to be distributed across the landscape because there's lots of rangeland that's relatively close to these landscape scale thinning treatments where we can have sub 100-mile transport distances and scale up to the needs of that thinning treatment. We look at wood vaults as complementary to sequestration sites and other bikers technologies that produce CO2 and inject it or produce bio-oil for injection. And we see big synergies between land conservation, both range and forest land conservation, and mine reclamation. And we are digging into those. There's lots of interest among within the conservation community that we've heard relative to the potential to offtake biomass from these thinning treatments. And then just this, in closing, I think it's really important for us to move quickly, but it's also really important for us to move carefully. And we're thrilled to be partnering with the Yale Carbon Containment Lab to further the science of woody biomass burial. I think these sorts of partnerships are really important to doing things responsibly and inviting a lot of scrutiny onto these projects. And finally, just a note from Kodama, if you are working on a compelling bikers technology, we are not indexing too hard on wood vaults. You know, we've come out as a biomass burial company in some articles recently, but we're much broader than that. We're focused on forest restoration. And so anything that we can do to utilize biomass in a high value way, we look at that as a win for forest restoration, and we look at that as a win for climate. So please come to us if you have feedstock supply needs in the future. And we are happy to entertain conversation about helping you to support your bikers technologies. And with that, we're happy to answer any questions.
Great, great presentation. Thank you so much. We love to kick off the Q&A period just by hearing a little bit about you guys, the presenters' personal journey to where you are now. Can you just get a couple minutes about how you came to the work that you're doing now, specifically carbon removal, and then specifically within carbon removal, biomass burial? Sinead, do you want to start?
Sure, yeah, thanks, Toby. So I started my PhD in 2016. My background was experimental ecology and coastal systems. As part of my graduate work, I was totally focused on interactions between crabs and grass and mussels and snails, and was very knee-deep in the mud about those sort of very specific questions. And I think one of the reasons that I pivoted from concretely academia to this more applied field was I do think that climate change is one of the greatest problems that we need to collaboratively address. And the Carbon Containment Lab brings together a wide range of expertise. So my background is in experimental ecology, but we have geochemists, we have folks with background in investing and sustainability and biochar and a wide range of fields. And so my move here was primarily to really think through how can the work that I do have the greatest impact. And so just in terms of why biomass burial to start with, as I mentioned, we were founded in 2020. And in those early days, it was, 2-3 of us in an office. And one of the, it was a particularly bad wildfire season in the American West in 2020. And so we did a lot of thinking about this particular issue and identified through that modeling that I talked about sort of that this is a large potential source of CO2 that could be emitted into the atmosphere in the decade or potentially utilized. And so we spent a good sort of year or so thinking about the different ways that that carbon can be contained, both in the shorter term, so thinking about slowing its decay such that it can be available for different types of bioenergy production, but also longer term in pathways such as burial. And so through some of that initial work, we met up with Jimmy and Merritt at Kodama Systems. Will also just mention that we have a series of experiments that we deployed in 2020 across a range of environmental contexts and with different sort of treatments of both above ground, encased treatments, and below ground. And so these will be experiments that are harvested every 2 years for the next 4 more years. And so I think we're really invested in understanding what biomass pathways can be utilized, particularly in the context of these overstocked forests. Jimmy?
Yeah, thanks, Nate. Yeah, my path here was really, maybe I'll start in the mining industry and then move backwards. So, I worked in mining for 6 years. And as Megan mentioned, I was working on water mass balances. So I could go to these mine sites and essentially constrain where all of the different elements that were leaching out of certain mine waste materials or heap leach piles or that sort of thing were kind of moving around on site. So I was doing these these systems models, and after working for 6 years for mines all over North America, I left that and started my own kind of boutique consulting firm, and found myself just diving really hard into carbon removal because it was like the ultimate mass balance problem that was directly tied to climate change. And I found it just really fascinating. And so I looked at a bunch of different CDR technologies, from DAC plus storage to mineralization to, I was reading Under a White Sky by Elizabeth Colbert and came across a reference to Ning's work actually. And so I called Ning up one day or sent him an email, and ended up corresponding with him quite a bit about woody biomass burial. And I thought it was really just kind of understudied. There's seemingly really good opportunities to pair both carbon removal with mine reclamation and landscape restoration in the West that in really beautiful ways that match liabilities. And then I'll just draw in that, I'm a really avid outdoors person. I do a lot of climbing, running, skiing. And when I can't do those things in the summertime because there are west-wide smoke waves, that is one of the problems that I feel most acutely and physically and painfully, as I know so many other people do in the West. And I really came at this with the idea of being able to make an impact on the wildfire problem via these forest restoration treatments, which I believe can make a really big difference. And it's not unbelievable to say that if we do things intelligently and we work with the right incentives in markets, that we could end or at least control megafire in the West. I do not think that is an unbelievable assertion.
Excellent. It's really great to hear these stories, I think, for everyone. And, I think as Peter Reinhardt from Charm Industrial often says, in a new sector like carbon removal, the distance to the frontier is short. And so, I think just get involved, and there are many different things to work on. And, we need to work on a range of pathways. There's so many audience questions. I'm going to cut short my usual Q&A, but just one question. And I know that this is also in your Excellent Frontier application, which I put in the chat, and everyone should take a look at if you want to learn more about what Kodama and Yale are doing here. But can you guys speak a little bit about how you think about equitable deployment and environmental justice with respect to wood vault? It's such an important topic across CDR. And, if you're talking about digging a hole and putting wood in it, you're like, what is the environmental justice dimension there? But if you break down the process into its component parts, you're rolling a lot of trucks, you're disturbing landscape. So can you just walk through a little bit about how Kodama and Yale think about this issue? Just, a couple minutes.
Yeah, absolutely. Sinead, maybe I'll start with this one.
Yes, please.
Cool. So I think we look at, first I'll just say, I think we look at the wildfire crisis is like a real driver of inequity in the West, and the people who are bearing the impacts of fire are many times underserved and marginalized communities. And so the more that we can do to address that problem, the more that we can do to kind of ameliorate harm to those communities. But the deployment of wood vaults is not. There's a lot of land questions that I think are the biggest, or one of the biggest sort of concerns that we think about and we try to engage stakeholders on. And those land questions are mostly around siting and around where would it be fair or reasonable or just to site these wood vaults. So doing this, within a community is not something that we'd ever, right smack dab in the middle of the community is not something that I think we'd ever really seek to do. And instead, we're looking to partner with both public agencies who feel these needs for forest thinning to develop these on potentially on public lands in the future, or to develop them in concert with conservation goals and to really drive towards conservation. And I think it all is going to boil down to a lot of conversation, a lot of stakeholder engagement, and a lot of planning and consultation with communities where these things happen. What I've been surprised by is that in early conversations with communities is that they just want the fuels out of the forest, and they want these landscape thinning treatments to happen because there's a direct catastrophic potential for loss to them. But I think within that, there's a potential to act rashly and act unfairly. And so we're trying to engage across multiple stakeholder groups and really go to environmental and community events where we can engage community members to ask, hey, how is this a bad idea, basically? Yeah.
No, I think, sorry, Sinead.
No, go ahead. I think, Jimmy, you covered most of it. I just think the one thing I'll add is just consent-based siting is something that the CC Lab has been thinking about across all of our projects. And we're learning a lot, but I think that really has to be at the center of any of these projects, especially where we're disturbing the land. So I think that's just the one thing I wanted to add. Back to you, Toby.
I think that, and that's a consent-based siting is an excellent term. I put a link to the Carbon 180 X Prize work. It's called From the Ground Up. It's sort of a playbook for how carbon removal practitioners can be thinking about this. And I think the title says it all. Like, let's make it foundational and let's do it first. Have a community meeting before you settle on a site and consent-based siting. And it's both the right thing to do. It's also commercially the right thing to do, because you don't want to be deploying in a place where you're not wanted. It just complicates things so much. So I think that, like, From the Ground Up is really a great precept for talking about this issue. And I think Kodama and Yale are doing a great job with it. So compliments to you both. And I'm going to flip it now to Mega. We have so many great audience questions, and want to like hand it over and let's cover as many of those as we can in the next 10 minutes or so.
Cool. Yeah, I wanted to start off with one we got from quite a few people, which was, can you just walk through very quickly, like, when it comes to biomass, your approach versus bio oil versus biochar, are there like pros and cons to each? Are they complementary? Is your approach, would you say it's better? Kind of, how do you compare them?
I mean, I can jump in here a little bit. I think that no one of these approaches is better. I think that they're all in the sort of tooled chest of what can be deployed. I think that there are pros and cons to each, though, in that, so for example, we're not doing any conversion process. So compared to things like bio oil and biochar, it's likely that our end product, the biomass itself on its own, is less durable. So it requires a much more stringent, controlled, and measured storage pathway. And so I think that there are some of these levers that you can toggle. I think with biochar, you can have some very significant co-benefits potentially. And so I think when you approach these systems, it really does have to be a little bit site specific, both related to the feedstock that you're considering and also related to the storage opportunities and also the sort of potential effect of the co-benefits. And so I think, just reiterating, I think there's room for all of these approaches, and it's just about the sort of natural history context of where you're deploying them. Jimmy, anything to add?
No, I think you did a great job there. Yeah, thanks.
Cool, thanks. A couple of people asked about the vaults themselves. So can you just talk through like the cost, the permitting side, who takes on the cost of it, any other considerations around actually building these vaults? And also we got a question on, I guess, how you think about scaling that up over time.
Yeah, absolutely. Maybe I'll jump in on this one, Sinead. Thanks. So yeah, the costs are, as I outlined in that second to last slide for our pilot, we're selling at around $600 a ton to Frontier, and we're looking at sub $100 a ton costs at scale. There's a number of factors that go into this. We've modeled a wide range of costs. I think NING's reported costs of 18 to 20, or like 18 to $40, something like that, 20 to 40, call it. We think this has the potential to be one of the lowest cost solutions talked about out there today. But that is really context dependent and site dependent. And the biggest cost drivers are really transport is the big one. How far you move biomass. Biomass is heavy, wet, and bulky, and transporting a lot of it is going to require a huge midstream supply chain. So we're really thinking about that and how to make that more efficient and service other biomass end uses as well there. So that deals with the cost. What were the other questions there, Mega?
Permitting, and then just like, how do you think about scaling up?
Yeah, so permitting, I talked to a lot of other biomass burial practitioners out there, and in the United States today, you need typically a class 3 or non-hazardous waste landfill license or permit in order to build a wood vault for commercial crediting. And that to me seems pretty reasonable, actually, because currently, there's no real policy mechanism for carbon storage on lands, and we need to prove out this technology before we start developing these all over the landscape, and that's what we hope to do with our demonstration project. That's what we aim to do with our demonstration project. I think one thing there's some concern about like risk of characterization of these as landfills. And one thing that's underappreciated in talking to the waste management experts that we get the pleasure of working with is the US is really, really good at developing waste management facilities. And, municipal solid waste facilities are shooting off methane emissions. A lot of that is not so good. And I'm not trying to give the impression that landfill, like burying trash is like the best, going down a road here.
Yeah.
Let me get back to it. I think there's important to keep things under easement for long term, like a legal and vault protection strategy is important. Landfill regulations have these easement and vault protection strategies. It's sort of inherent to them, and so that's the right permitting structure for now. But we think in longer term, we're going to need policy change if wood vaults turn out to be a great solution. And that policy change would look like something more like mining materials and the storage of mining materials for long term, which is outside of conventional landfill regulations in the US. And this would be maybe a carbon storage function for wood vaults specifically, and some regulations associated with that. There's also low-level radioactive waste containment and disposal facilities are regulated separately from landfill regs, and that is explicitly tied to durability. So there's a minimum design life of 1,000 years and a functional life that's much longer. So something like that, a regulatory sort of structure like that might be more appropriate for long-term wood vault deployments instead. So that's kind of the permitting policy side. For our pilot project, we're aiming to permit in conjunction with the local landfill and actually develop near a thinning treatment in Eastern California. And we are going to be developing it on a small undisturbed parcel at their facility.
Cool. In terms of your kind of analysis that you showed of like how you picked where were good places to do that, how applicable would that analysis be to other parts of the world? This person asked about Europe, and how do you think about potentially doing that sort of analysis elsewhere?
I think that's a great question. I think though it's dependent on the data that's available. I think it would also involve just understanding what practices are in the country of interest. So I think the assumptions that we made were based in conversations with experts actually doing the work. And I think that at the county level, it's a good sort of understanding of the average and sort of highlighting regions, but really you'd want higher resolution interpolated data in combination with a really sort of, in-depth understanding of what the actions undertaken would be. So would be thrilled to talk with folks if they want to extend this analysis, and happy to share code and data and sort of approach. But I would just be cautious about direct application.
Right, okay. Someone was asking about kind of like the nutrients and minerals and other things that end up getting buried in addition to the carbon itself. So how do you think through the mineral depletion, and especially I think phosphorus is particularly an issue. How do you analyze and mitigate any issues around that?
Jimmy, you want to take it?
Sure. Yeah. So we're focused on small diameter wood right now. So the wood only, not the branches and needles where most of the nutrients are held. So it's largely carbon, hydrogen, oxygen, and nitrogen that is in there. And there's actually quite the trace minerals and nutrients are not really significant in the wood, especially because most of this stuff is just going to be pile burned or removed and combusted about energy facilities. Well, not a huge amount of that is actually happening, but we don't have too many concerns relative to the scale of the concern and risk of landscape conversion and fire risk generally. So we look at this first as increase in pace and scale, and then we look at the magnitude of the other kind of nutrient depletion problem as being really small. I think it is more significant in ocean environments or agricultural environments where you have higher uptake of nutrients than you would have.
Right.
I would also say, sorry to interrupt you.
Yeah, no worries.
From the point of view of the Carbon Containment Lab, this is one of the reasons that we're focused in the American West, where this biomass is already going to be thinned, and the business as usual is to pile burn it typically. And so in other contexts where that biomass would be more distributed and slowly decomposing and is an important part of the nutrient cycle, I think that's a different story. And I also think you do have to keep in mind the disruption to the soil carbon. So in the areas that Kodama is currently focused on, it's all less than 1% organic carbon in the soils. And so I think just, again, driving home that you need to be diligent about the context. And in that, once you are, I think you can sort of move forward knowing that the disruption is warranted.
Cool. I'm just going to close with one last one. Just a couple of people threw out some interesting ideas, and I'd love to hear your take. So one was using Christmas trees, 25 to 30 million every year in the US, and doing something like your process with that. And the other was sort of taking advantage of like natural disasters. So this person mentioned Austin's ice storms downing 100,000 cubic tons of tree limbs. What do you think of those two ideas and kind of extending beyond your current scope within forestry?
Yeah, so I think a lot of it has to do with the counterfactuals. What happens to that material instead? And there needs to be pretty thorough analysis of what happens. So if most of those in Austin, if most of those tree limbs are being air curtain burned, that's a combustion counterfactual. That's fairly strong. Christmas trees, I'm not sure what happens to them. Maybe some of them go to landfills, or in fact, I think they'd have pretty good carbon storage. But then it's got a lot of branches and needles, which might create more degradable organic carbon and more methane. So there's just a lot of math that needs to happen for every single one of these. So we're really focused on the wood vault from the forest thinning project because we kind of have all the parameters defined there. But I think these are great new markets for people to think about. And if you have desire to pursue biomass burial in any one of these projects, I'm happy to serve as a resource and chat with you about what some of the counterfactuals might be and discuss how you might build up sort of a business model around that.
Yeah, and I know we can address all of the questions here, but if anyone has follow-ups or questions and they want to reach out, both Jimmy and I think are more than happy to continue these conversations offline.
Cool. Thank you guys so much. I know we're almost out of time. Sorry for everyone whose questions didn't get answered. And Toby, back to you to finish that.
Hello, everyone. Thank you to Sinéad and Jimmy for being with us. That was fantastic. Super interesting topic. I think a super important emergent wood pathway for carbon removal. And there are many different bikers pathways. Someone mentioned biochar in the chat. I think we can be pursuing all of these, see how they work, and then figure out, in 5 or 10 years, which are the best ones to scale further. So, but really great presentation, and thank you guys for being with us. A couple quick programming notes from us before we close, and let's see. One thing we want to talk about, and Mega, if you could put those links in the chat, that would be great. We have a bill that's being advanced in Massachusetts. It's actually S.2096 now. It has a permanent bill name, but the state level carbon removal procurement bill in Massachusetts. If you are in Massachusetts, we would love to get some help contacting your local representatives. We'll put some links in the chat, or you can follow the open air join link. But it would be really great. The bill has very good prospects, and we're kind of at the crunch time in terms of advancing it. This CDR has been on a bit of a hiatus, but we have a bunch of great stuff coming up this spring. A couple of these Eventbrites are live. A couple of them are Eventbrite person, which is me, have not done yet, but we have Capture 6 on April 18th. We have a couple of appearances from the folks at Frontier. On the 25th of April, they're going to come on with Carbon Plan to talk about updates to their really amazing verification framework. Kita, which is a UK-based carbon insurance company, will be on May 2nd. Insurance is really important to scaling the CDR sector. Frontier is back on May 9th to talk about their initial round of offtake purchases, which will have been announced by then, which is super exciting. And then May 23rd, we have a Berlin-based biochar X concrete company called Ecoloct. So a lot of great stuff coming up. Thank you to everyone for being with us. Thank you again to Sinéad and Jimmy for such a great presentation and discussion. Everyone be well, and we will see you again soon.